So today I'd like to talk to you about the use of minimally working programs in computational physics assignments. What are the opportunities that we have when using MWPs, and what challenges do we need to learn to overcome? So first I'll start out just giving you the definition of a minimally working program and some reasons for using those in your coding activities. Then we'll talk about some options you have for deploying an MWP. We'll talk about different ways you can structure a minimally working program based on what it is you want your students to be able to do, and the different ways you can use a minimally working program in a class. What I would like to particularly offer to the discussion is how we can support MWPs with pre-class videos to help our students get into the mode of thinking through these MWPs and learning how to read them, getting excited about using them in class, and then I'll outline a few remaining challenges that warrant further investigation regarding MWPs. So a minimal working program is an incomplete code that's used to start an activity. So print hello is sort of the archetypical minimally working program, right? It's one line, it definitely works, you can build a lot of other things from it. Students usually interact with MWPs in groups, so when we go through this, imagine students gathered around a laptop, or 6 feet around a laptop now, looking at a code that's already been written that has some information that is missing from it. An analogy to this, you can think of this as being like when your students come into a lab activity and you have already set up the lab equipment for them at the beginning, as opposed to having the students come in, get out all the lab equipment and setting it up. That would be analogous to the students writing their code from scratch. We tend to want to get to the physics in lab, so we tend to already have some equipment ready for them to go. So this is doing the same thing. We have some code already ready for them to go, so we can focus on the physics instead of getting bogged down in the weeds of writing the code. A minimal working program can really help the scaffolding process. So it takes students from reading code to using code to modifying code to then writing their own code, right? So putting novice coders in front of a blank coding environment and telling them to write a code from scratch can really be a challenge and really can overload them. So this is trying to scaffold them up to there. The goal is to shift students' focus away from the syntax error, so the error messages, onto the physics. So does the code reasonably model a real world problem? And of course, this all helps us to avoid writing the code from scratch and get straight to the physics. Because while the coding is important and it's a valuable skill, we do want to teach some physics in the midst of all of these programs that our students are working with. So when you want to provide your students with a minimally working program, you want to decide on what venue you're going to use to deliver that MWP. So one option is if you have a course page or a learning management system, you can simply post a link to download the file. This is pretty straightforward, and you've got you can simply send the link to the students. But downloading things and working with installed software is not a forte of this generation of students. So that's where platforms like GlowScript and Trinket come in handy. In GlowScript, you provide a link to the code. It appears in a web browser. There's no installation necessary. Students just edit it directly and run it in the web browser. Then when students want to edit your code, they have to take yours and copy and paste it into a blank code in their own folder. Trinket works very similarly. You can provide a link to the code, or you can deploy it within a Trinket course. So you can have an entire course page that's got your class notes serving as your textbook, and then you can have embedded images, embedded videos, and you can have this code screen here embedded right there in the course page, so the code is actually part of your course materials and not a separate page that they're going to. This is what a Trinket screen looks like. Half of it is taken up by the code, the other half is taken up by the animation window. So the trade-off for going from GlowScript to Trinket is the screen real estate. GlowScript lets you focus on just the code or just the animation. Trinket, you've got the code on one half competing for real estate with the animation window. The other slight difference is instead of copying and pasting the text of the code on Trinket, students click this remix button, so they are saving a copy of it. So that's a little bit easier procedurally for them until they have to go and locate their files, and they have a little bit of trouble with that sometimes. So GlowScript versus Trinket is largely an aesthetic choice. It's usually your preference. This is what a Trinket course page looks like. As you can see, I've got some instructions for the students here. I can use some markdown formatting. It also allows you to format using LaTeX. So you can turn your Trinket course page into your textbook with interactive code, and it's pretty great. Another option, if you're working with more advanced students and you want to use Jupyter Notebooks, Jupyter Hub is a great place to collect and disseminate your Jupyter Notebook files. When you think about building a minimally working program, you can kind of think of it, again, in terms of scaffolding about what you want the students to do. So a very basic way to write an MWP, in fact, this might not even be technically considered an MWP, is you give the students a fully functioning code and they simply change the numbers. So this is where you're treating it kind of like a PhET sim, where you're letting them see the coding underneath the hood there. So as an example, let's suppose you're conducting a gravitational motion activity with a planet going around a star. This would be the students open the code and they enter the masses and initial velocities of the planet and the star, and they run the code and see what happens. One level deeper from that is you give the students a fully functioning code and they add features to it. So this could be, you have your gravitational motion code, the planet's going around the star just fine, but you want the students to add graphs of kinetic energy and potential energy versus time so that they can watch the conservation of energy process in action. Another step down, you can give them a technically functioning code, meaning it doesn't produce any syntax errors, but the students need to add the physics, right? So this is something like the planet initially moves in a straight line and doesn't deflect due to gravity because you've set the force initially equal to 0. This is the most frequently used version of minimally working programs. This is what most people mean when they say minimally working program. Basically, what you do is you remove from the code the thing you're trying to assess knowledge of. So if you want to see if students know how to calculate a gravitational force in space, you take out that force, replace it with a 0, and tell them to add the piece of missing physics. Another thing you can do is you can introduce a mistake into the code. Usually a physics error is what we have in mind here, not a syntax error, that the students have to identify and fix. So this could be something like you give them the gravitational force, but you make it a 1 over r to the 4th instead of a 1 over r squared. And you have students investigate where the problem is. Another thing, if you're looking to assess students' ability to logically process through the code and understand error messages, you can give them a code that is throwing an error and they have to add maybe some missing piece of code. So like maybe you're using your gravitational force here and you omitted the definition of r hat. Then once you have the students in class and they have the minimally working program in front of them, there's several different types of activities you can have them conduct depending on the amount of time you have or the learning objectives for that unit. The first option is students can predict how the code should behave versus how it will behave. This is especially useful in that case where you've omitted the force or you've got the wrong kind of force. So the students have to engage in physics reasoning alongside of reading the code, predicting both outcomes and seeing where they differ. So this is something like you predict the trajectory of the planet around the star, and it turns out actually that this type of prediction is a skill that has to be taught. So if you use this, you want to kind of train your students how do you make predictions based on the physics and based on the code and not kind of intermingle the two and actually compare the two. Another way you can use a minimally working program is to require that the students' code match real world data. So you give them this gravitational animation code and the students have to model the sun and the earth has to get around the sun in 1 year, right? It's an answer that they know has to happen at the end, and so they're able to check their own work. The students can also explore concepts through examples. So this could be something like the students demonstrate and then explain conservation of energy. So maybe they create those kinetic energy, potential energy, total energy graphs, and they have to explain any discrepancies there, maybe related to the time step, maybe related to a mistake in the force calculation. The students can also explore the varying degrees of accuracy in the code. This usually, for intro mechanics, amounts to changing the time step of the code and seeing when the answers smooth out. They can also extend the problem being studied. So maybe you start out with a planet going around a star, and then you make it a planet going around a binary star system. And suddenly they've got to add more objects and more forces and more update equations. Students can also modify the MWP to study a new problem. So maybe you finish the unit on gravitational motion. The students feel pretty confident about that. And then you ask them to replace the gravitational force with the electrostatic force, and then they can start exploring electrostatic repulsion as well as attraction. Now, all these activities are wonderful and helpful, but they all kind of assume that the students are able to come to the minimally working program, read it, and understand it, which sometimes takes them a while. That's actually a big learning hurdle, is them actually understanding what the MWP does to begin with. So I've begun to supplement my MWPs with pre-class videos to help introduce students to the next program that we're working with. So reading a code and working with it is a game. This is kind of teaching them the game. This is why I call my YouTube channel Let's Code Physics. It's modeled after Let's Play channels. So things that students need to be guided in is looking for where the physics is. Not every line in an MWP actually contains physics. Some of it is just bookkeeping or setup. Another question they need to look at is, how is the physics used? Students will very frequently entangle the physics with the coding. So all that, bookkeeping, variable, graph creation stuff they think is just as significant as the momentum update. It also helps demonstrate where they need to focus their attention. For example, comparing the initial condition versus the loop in the code. As experts, we tend to look directly at the loop because that's where the physics is taking place, and the rest we know is just setup. Students do the reverse. They tend to focus on the initial conditions because that's where they see all the real numbers, versus the loop where they just see a bunch of letters and they don't ever, get around to getting down to that part. They also need to learn to examine what does each step in the MWP do. Spoiler alert, students do not read the comments that you leave, so you can think of this pre-class video as sort of a running commentary on your code. This can help you do things like reinforce that they need to read the code in order. Students do not naturally think of a computer code as a set of instructions happening in order. They tend to think that it's all happening all at once. They need to distinguish between defining a quantity versus using a quantity. And this process likely has to be repeated because this is a new way of reading that the students are learning. These pre-class videos can also help students to start thinking of applications. It's amazing when you give students an opportunity to get to know the MWP before coming to class. They come into class already having ideas that they want to try out, already having example problems that they want to apply this to. So a pre-class video can accomplish several objectives. It can help you review the physics. It can show you developing the minimally working program. You can take students on a tour of the MWP, emphasizing the computational strategies you're wanting them to learn. You can use the video to map the algebra that you're using onto how it's implemented in the code, because those don't always look the same. You can show the students yourself using the MWP and how you would use it in an activity or in a research setting. And if you're putting this pre-class video up on, say, YouTube or another hosting platform, you can just include a link to the minimally working program or integrate both the video and the code onto your course trinket page. And so using these pre-class videos, you can ask warm-up questions of your students, and students can begin trying out the code already a little bit experienced with it when they come into class. So I've made many of these pre-class videos about MWPs. I host them on my YouTube channel here, Let's Code Physics. You are welcome to use those videos if they fit in your class as well. Let me show you just a couple of examples. Here's a screenshot from a video introducing students to the Euler-Kromer method. Here I'm trying to emphasize the strategy behind the Euler-Kromer method. I want students to not worry so much about all the numbers that are being set up or all the graphs that are being used just yet. I want them to focus on the central engine of the Euler-Kromer method, this momentum update and position update. I'm trying to help my students see that these have the same form, that they're the new value equals the old value plus the slope times the step size. So I'm trying to emphasize that here visually by highlighting these two and showing this kind of generic equation off to the side. This is something that I would do in class if I were introducing it, but by pushing it to the video, I'm hoping that the students will kind of internalize that before they show up to class so that they start to look for this structure. Another example here is a couple of screenshots from a video about gravitational motion, like we were talking about earlier. So I'm trying to help students distinguish here between where I set up the planetary system and here where I use the planetary system. So here we're outside the loop. We're setting up a star and 3 planets, and I'm just trying to help the students see that this is where you create these things. That doesn't mean they do anything. It doesn't mean they automatically move. I'm explaining to them in the video that this is where you create your solar system. And so on the assignment, if I ask them to go in and create their own solar system or add a planet, this is where they need to go. Here I'm trying to communicate to them that the force on planet 1 is only affected by the other objects interacting with planet 1. So for example, here I'm trying to highlight that that in the calculation for the force on planet 1, there is no force between star and planet 2. There is no force between planet 2 and planet 3 because planet 1 is not involved in that. And so I'm taking that opportunity to make that point there so that I hopefully don't have to remind them of it so many times in class like I usually do. So minimally working programs are great. There's a good body of literature on developing them and using them, but there's still some questions that we need to think about. So do students actually learn how a minimally working program works, or do they just learn enough to complete the activity and then move on? Do skills and understanding that the students develop really carry over from one activity to the next? I ask this question because it seems like my students, I don't know if this is anybody else's, but my students seem to start over each week in terms of remembering what a loop does, or remembering how to create a graph, or remembering what the update equation is. They seem to reset their knowledge every time they open a new code. And students, I've noticed, don't seem to voluntarily use computational techniques, meaning if you give a student an open-ended problem and you say you can use any method you want, they tend to still go straight for their paper and pencil solution method, and they don't spontaneously go to a computer code. So that's kind of I think the next step we need to start working toward is how do we train students that this is a valuable thing that you want to use in your professional and academic work. So thank you so much for your time.